Alrighty then, corn children. I'm gonna throw some theory down on you today. It is the volume of revolution using the washer method, part 1. Alright, so what the heck is going on here? Alright, here's what we have. This is the curve F. Now, I haven't even put the variable in here, but this is F. Here is G. F and G are forming an area, a bounded region. They are intersecting at A and at B. Now, we're going to take this region right here and we are going to revolve it about an axis of revolution, y equals something, K. We're just going to call it K. Now, first thing I want you to notice, I have drawn you a rectangle to represent the area based on Riemann sums. I have a representative rectangle. If the axis of revolution is horizontal, then your rectangle is vertical. They need to be perpendicular. They must be. For the washer method, you're drawing it perpendicular. So horizontal axis of revolution, perpendicular rectangle. All right, now here's part of the gig. Once I have this rectangle drawn in, you're going to notice that the width is a small change in x. The second you have a small change in x as opposed to y, then there are certain things you're going to need. Our limits of integration need to be found on the x-axis. This axis of revolution here is not necessarily the x-axis, but I could drop this a and b value down to the x-axis. If this is with respect to x, g needs to be a function of x, and f needs to be a function of x. All right, now here's the gig. We're going to take this rectangle and revolve it. All right, stay with me. My drawing skills are something. When we do this, this bad boy is going to rotate all the way down and around like so. Yeah, these are mad artistic skills. But here's the gig. Do you see how the bottom of this rectangle is not sitting flush on the axis of revolution from A to B? It's not even touching it at all. It could be, but it's not sitting flush. So as this spins around, there will be a hole. Yeah, I have to concentrate. Shh, she's concentrating. A hole. Wow, that's really awesome. Hey, me. There's a hole in our disc. It's not a disc. It's now a washer. That is a disc with a hole in it. Hey, look what I found in my basement. Yeah, that's what we're making. Or, look, I found another one. We're going to fill this region with all of these rectangles, and when they spin, we're filling up the volume with these washers. And we need to find the volume of the washer. Well, the good news is it's just the big outer disc take away the little skinny inner disc. So it's basically big disc method minus little disc method, and we just kind of crush it together. Now, I'm going to try to help you out though. Here's the gig. All right. We need to do the outer disc first, the outer farthest disc. So we need to find our outer radius. Well, let's do this. In order to find your outer radius, here's what I want you to do. Do it. Don't even argue with me. Put one finger on the axis of revolution. Put your other finger on your rectangle as far away as you can go. Your top finger is sitting on something. Your bottom finger is sitting on something. If you do top minus bottom, you will get your outer radius. All right, so here we go. Axis of revolution, farthest edge of the rectangle. That is capital R. It is a function of x because of that dx. and it is the top curve f of x minus the axis of revolution k, top minus bottom. That's your outer radius. Now, over here, put your finger on the axis of revolution, do it. Put your finger on the closest edge of the rectangle. You are now touching the ends of the inner radius, the little radius. And this is again top minus bottom. Your top finger is sitting on the g of x curve, and your bottom finger is on the axis of revolution k. So this right here, I'll move it over, is little r of x. And in this example, it is g of x minus k. So now that we have our radii defined, here's how we get the volume. Our volume will be, now each of these is going, the rectangles are going from A over to B. That's where the region is. So it's going to be integrated from A to B. Notice that these are on the x-axis if we drop them to the x-axis. We are spinning these things and finding disks, so it will be pi, the outer radius squared, I'm leaving some room, with respect to x. This is pi r squared h. This is the outer disk. Now all we have to do is subtract pi distributed through little r squared with respect to x. This is pi r squared h, the inner disk, and we're just subtracting them. Now listen, let's not be crazy. Each of these is squared independently. You can't do big R minus little r all squared. That's wrong. It is correct to have the squares on each part. Now, in a future lesson, something to look forward to, we're going to do this whole thing again, but we will have a vertical axis of revolution. X equals k. We will have disks that are, or washers that are spinning this away, set up perpendicularly, and it will be a small change in y. And this will be g of y and f of y, and the radii will be functions of y. Because that's what makes it work. Yeah. So, enjoy that theory. There it is. Hey, touch the paper with your fingers. It helps. I'm not even kidding.